Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys have been having a good week. Let's actually jump into it. We have a test tomorrow. It will cover everything that we did up until Monday. So hopefully you guys are all ready for that. And I'll talk a little bit more about office hours afterwards. Let me share my screen here. And let me make sure that I can see the chat and everything as well. All right. So in the meantime, we are going to continue with our series discussion, and we will forge ahead. Let's see here. Maybe I should do a quick recap. Let's see. What do we know about series so far? So just a quick recap. We know about what series are, hopefully by now. A series is just the sum of the terms of a sequence. So you have a list of numbers in some order that can be determined. Now what you want to do is you want to add up all these numbers. And it's particularly weird to do this in the case where you have an infinite list of numbers. And so that's the case where we really need to work out. We figured out that if we define something called the partial sums, the sum so far at some point, we can actually think about the infinite sum of terms as the limit of the sequence of partial sums. So we have that definition. Using that definition, we figured out how to add a half plus a quarter plus an eighth plus blah, 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 going on forever. So that was pretty neat. It added up to what we expected it to be, to add up to a mile, 1 unit, which was a mile in the story that we were using. So that was pretty cool. A couple important definitions. There are a couple ways that an infinite sum can add up to make sense. One way is we can talk about a sum converging absolutely. That means we take an infinite sum, and if I put absolute values around all the terms and I add those guys up, it converges by the previous definition. There are times though, however, when a series, if I add it up, it'll converge, but if I put absolute values around all the terms and then add it up, then it will no longer converge. Those guys, we say they converge conditionally. It's important to know the difference because the ones that converge conditionally don't play along well with the math rules that we're used to. So commutativity of addition is no longer true for a series like that, which means you can rearrange the terms and change the answer. And so that's not good when we want to do things in calculus like distribute integrals across sums and then calculate one integral at a time. It turns out for a conditionally convergent sum, it means that the order in which I do the integration will change the answer, which shouldn't make any sense. So knowing when something is converging absolutely versus conditionally is going to be important, and we'll talk about that in a bit. We saw some properties of sums. In general, you can kind of factor constants out, and you can distribute sums series across summations. They do not distribute across products. That was very important. Telescoping series, very important types of series to know about, but we're super important, but it's a cool kind of series that you can know about, but we're not going to talk about it. That brought us to the next section where we talk about series convergence tests. So we saw the example of where we added up all those terms and we got 1 as the answer, but it turns out that that process is kind of annoying in general, like for you to figure out, okay, what is the general formula that describes the partial sum so that I can take a limit of it? It turns out that it's actually, in general, it's very hard to get that method to work out. So we developed some series convergence tests. So these are the tests that will tell us that a series converges. They may or may not tell us what the series converges to, but they can tell us that it converges to something meaningful. Like if I could find the sequence of partial sums, then I could take the limit and I could get an answer. But we might not know what that answer is specifically, but these tests are going to determine if such an answer exists. And this is actually also useful. The fact that they don't give us an answer is unfortunate, but it doesn't mean that we can't continue because we have approximation methods. So we can actually approximate answers very well once we know they're there, but we need to know that they're there in the first place so that it's worth us attempting to approximate them. So yeah, that's where the series convergence test comes in. Only two of them that we will talk about will actually tell you what the series converges to. That is the geometric series test, as well as for telescoping series. But all the others, they don't tell you that a series converges. They just tell you whether or not something converges, and you don't know to what it converges. Figuring out to what it converges is a lot more complicated in general. Yeah, so these are the tests that we are going to know, and essentially I'm going to go through them one by one. And last class, I actually went through one of these. This was the divergence test, the guy in the second row here. So we're just going to continue the discussion. I'm going to talk about all these tests eventually. So the next one up is going to be, I'm actually going to do the geometric series test first, and then move on to the integral test, etc. So yeah, that is what we are doing today. We saw the test for divergence was the first one. This basically tells you when something diverges. It cannot tell you about convergence. Very important. Students often forget that. If you're taking the series, you want to take the series of a bunch of terms, and the limit of the term does not approach zero, it means that the series will diverge. If the limit approaches zero, you don't know. It may diverge, it may converge, and we looked at two examples that can show you can go either way. So for both of these examples, the limit approached zero, but one converged while the other didn't. So if the limit equals zero, means nothing, right? You have to do further tests. However, if the limit is not zero, right? If it's anything other than zero, then we know for sure it diverges. So this is called the test for divergence. Very important test in the sense that it's one of the first things that you will always try. So if I give you a list of series and ask you, do these guys converge or do these guys not converge? One of the first things you're going to look for, you're going to eyeball is, okay, if I take the limits of all these things, would they go to zero? Because if the answer is no, then they won't converge. So that was the test for divergence. Yeah. So continuing with this, we're going to move on to test number 2, the geometric series test. So a geometric series is a series of a geometric sequence. So there is a sequence called a geometric sequence. Okay. So a geometric sequence is a sequence of this form. So this basically tells you the first term is A, then you multiply that by an R, then you multiply that by an R again, then you multiply that by an R again, then you multiply that by an R again, and continue. So if you create a list of numbers like that, you start off with a number, and then to get each successive term, you keep multiplying by the same number again. You develop what's called a geometric series. As for why it's called a geometric series, I linked you to something here. It's actually linked to the geometric mean, which is a whole other thing, but you don't need to know about that. But just in case you're curious, you can check that out. But a geometric sequence is a list of this form. Start out with a number and then keep multiplying that by the same number over and over. So if you start out with the number A, you take another number R and you keep multiplying by R, you can generate a list in this way. And this list is called a geometric sequence. Now, ever so often, we'd like to add the terms of such a sequence. This gives rise to what's called a geometric series. So that leads us to the definition of a geometric series, which is right here. So that's very important. You can take a picture of that or just remember the picture. And I think I shared these notes with you guys already, so you guys have this. So one thing about the geometric series, it has a very specific form. There are a couple common ways in which we see these guys appear, and it depends on whether you're starting the counting from n equals 1 or n equals 0. At the end of the day, you do want the first term to be A. So if you're starting from n equals 1, you want the power to be n minus 1. And if you're starting from n equals 0, you want the power to be n. So that when you start by plugging in, the R value has 0 power. And so you only get the A in the first term. So it's very important that you get the A in the first term. Both of these guys are going to go off to A plus AR plus AR squared plus AR cubed plus dot, dot, dot. Okay, so you want to make sure that they start at A. Another thing that I would want to call your attention to, and I think I put this in the notes, but let me just write it down here as well. So one thing you should note is that A and R are non-zero and they are constants. This is very important. So when you're looking at this form, the series of AR to the n minus 1, or the series from 0 to infinity of AR to the n, how do you know it's geometric? The A and the R have to be constants. If the A and the R are not constants, then it's not geometric. And when I say constant, I mean with respect to the series, meaning they don't have any n values in them. They can have other variables in them, but as far as the series is concerned, it's constant if it doesn't have n, right? So this is constants with respect to the series. Okay, so that's going to be important. So you need to be able to identify these things. And one thing that is very straightforward to identify, well, can be a little bit challenging to identify, but it's something you're going to be looking out for, is a geometric series, right? So that's these guys, okay? So like I said, the series looks like this when you start multiplying out and adding all these terms together, right? Now, it turns out that we can know when these guys converge, and there's a pretty cool story. It's actually very similar to the story that I told my Calc 1 class that you guys may or may not remember. I don't want to actually spend too much time on this, but there was the story about how a very famous mathematician called Gauss, when he was a very young child and he was in preschool or whatever, and his class was kicking up a ruckus, and the teacher was like, "Okay, everybody, quiet down. I want everyone to add all the numbers from 1 to 1,000." Right? So the teacher, like stopped everything to get everyone quiet down and made everyone busy. Like, okay, everybody adds up all the numbers to from 1 to 1,000. And she basically thought, okay, that's going to keep them preoccupied for the rest of the day. Like these kids just basically now are just learning to count with little objects. And so, okay, there are 2 little toy trucks, 3 little toy trucks, right? So you have all these kids there in the classroom, counting on their fingers, trying to add up all the numbers from 1 to 1,000. And the teacher thought, okay, I have peace and quiet for the rest of the day. And lo and behold, a couple of minutes later, little baby Gauss walks up and gives the teacher the answer. Oh, here's the sum of all the numbers from 1 to 1,000. And it was very like, what? How did he figure that out? Well, little baby Gauss could do algebra and arithmetic when he was very young. So he actually figured out a little trick. So it turns out that he was like, okay, I needed to add up all the terms from 1 to 1,000. But he was aware of commutativity of addition. He didn't care about the order. He noticed that this would be the same as if he added things in the opposite order. Right? So he's like, okay, this is the thing I care about, S. This is the sum I care about. That's another way to write S. Another way, the thing I care about. Then he noticed that if he were to add in the columns, he always got the same number back, right? Notice that that's 1,001, that's 1,001, that's 1,001. So he basically noticed that by doing this little trick here, he found out that these things always add up to 1,001. And then he realized, well, if I added those 2 things, I'm really getting double what I want. Then he figured out, okay, well, how many 1,001s are there? Well, there are 1,000 1,000s and ones. And that is double what I want. And so the sum is really this guy, right? So that's really just 500 times 1,001, which is, 500, 500. So yeah, she gave them this task. Little Gauss figured that out. Like, here's the answer, teacher. And yeah, that she couldn't keep little Gauss down. Legend has it, the rest of his class are still trying to add up the numbers from 1 to 1,000 even today. Kidding. Okay, so that was a way to actually find this. And we all actually saw this in Calc 1. It was the way we derived that the sum of the first n positive integers was n times n plus 1 over 2 was actually the same idea. So if you have like 1, 2, 3, going all the way up to n, and that's your s, you realize that if you turn this around, then they all add up to n plus 1, and you would have n such terms. And so that would be 2 times s. And so you'd realize the sum of the first n terms would be n times n plus 1 over 2. Okay, so this is a trick that we've seen before. And it turns out that a similar trick can help us figure out what a geometric series adds up to, right? You can actually do a very similar trick, right? So recall that a series converges if the sequence of partial sums converge. So what we can do is try to figure out what does the sequence of partial sums actually look like? And we can actually play this little game. So let's say I have Sn, the sum of the first n terms of a geometric sequence. And then I can say, well, we're going to be a little bit different here. I'm actually going to multiply that entire thing by r. I can do this. It's a finite sum, so all my regular algebra and arithmetic rules work. Here I would get ar plus ar squared plus dot 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 plus ar to the n minus 1 plus ar to the n. Then I can, I'm going to look at these guys. And if I call this equation 1, call that equation 2, I'm actually going to take equation 1 and subtract equation 2. Notice that over here, I would have 1 minus r times Sn. And on the right side, if I'm taking the top and subtracting the bottom, this subtracts that, da, 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 goes all the way down. This will subtract that. And I would end up with a minus ar to the n. So now you can actually describe the sequence of partial sums as a times 1 minus r to the n over 1 minus r. Okay, so that's actually how to, that would actually give you the sum of the first n terms of a geometric sequence. Now this is considered to be the partial sums. So now this means that if I were to find what this guy adds up to, ar to the n minus 1, and goes from 0 to infinity, it would just be the limit as n approaches infinity of this guy. Now, what is that limit? Does anyone see what that limit would be? Remember, your a and your r are constants. Yeah, Stephen?
Can we rewrite it as a times 1 minus, well, it depends what r is, because I feel like if r is bigger than 1, it's going to be a problem.
Right, right. So you notice that you have an r to the n, and your n is going off to infinity, which means if your r is like 2 or 5 or 1,000, that's a problem, because now you have 5 to the n, right? That's an exponential. Also, even if your r was a big negative number in magnitude, like minus 1,000 to the n, that still goes out of control. Can you tell me what r values would we need to actually control?
If it was less than 1.
Okay. Just less than 1?
Or
I mean,
less than 1 and greater than -1?
less than 1 and greater than -1. This only makes sense if, so notice that this guy here, he diverges if our R is bigger than 1 in absolute values, or equal to 1, by the way. And the equal to 1, it's not because it causes a problem in the numerator. The equal to 1 causes a problem in the denominator, right? So you would get a division by 0. You can actually use something like L'Hopital's rule and show that that's actually going to go off to infinity. So it's going to diverge for anything that's magnitude-wise is 1 or larger. However, it does converge if my R is less than 1 in absolute values. Then this term here, the R to the n would go off to 0 in that case, right? And so we would end up with A over 1 minus R, right? So it turns out that any series of this form, we can know what it will add up to, and even when it would add up to something meaningful. So this leads to, I left some space here, let's snip this. The geometric series test. This is how you know when a geometric series actually adds up to something meaningful. So given a geometric series, a series of this form or that form, where A and R are non-zero constants, the series converges absolutely if and only if your R is less than 1 in absolute values. And I can say absolutely because I'm putting in the absolute values to get this thing to work out. So it actually doesn't matter if your R is positive or negative, as long as it's within between -1 and 1, not including 0, then we are fine. So this actually converges absolutely, and that's actually an important thing to notice as well. So if our R is less than 1 in absolute value, this will converge absolutely. There are a few tests that tells you about absolute convergence. The geometric series test is one of them. Things like the ratio test and the root tests are others. So whenever you're doing a test where it also guarantees absolute convergence, it's nice to know. So it doesn't mean you have to check anything extra. But yeah, if you have a geometric series, it will converge absolutely if your R is less than 1 with R in absolute values. And on top of that, we know exactly what it converges to. It converges to A over 1 minus R. You pretty much derive that using the trick here, right? So that's a geometric series. It's a new type of series, and that's a test that goes along with it. So let's actually do some examples. I have 4 examples here. Move these, get to them later. So let's go through some examples. First one, I don't know, it's kind of tough. Let's see. Actually, the first one is one that we've seen already. Notice here that this, if I started plugging in n equals 1, I would get a half. N equals 2, I would get 1 over 2 squared. N equals 3, I would get 1 over 2 cubed, etc. Right? So this is the same guy that we looked at with the dichotomy paradox. We saw that this adds up to 1 last time. Okay, but now I'm going to show you another way to look at this same series. Like if you didn't want to actually build up to what the partial sums look like and then take the limit, you had other options. Here is what you could notice. Here you can notice that this is the same as the series. I can factor off a half. And you might be wondering why would I factor off a half, but let's see if you see it in hindsight. This can be rewritten as a half times a half to the n minus 1. So again, I want to show that this is a geometric series. I need to get it in the right form. Notice that the series starts at n equals 1. That's the lower index, which means I need to have this series look like a times r to the n minus 1. So I need to write it as a constant times another constant to the n minus 1 power. So in their beginning, it did not look like that, but by me factoring off a half, I now get the n minus 1 power. So that actually ends up being this, right? And now I can see this is geometric. With my a is a half and my r is a half. And so I know since r in absolute values, well, that's just a half in absolute values. That's just a half, which is less than 1. It converges absolutely to a over 1 minus r. And so that tells me that this guy should add up to something meaningful. And in fact, I can tell you specifically what it adds up to. A over 1 minus r. Those are both a half. And so that's a half divided by a half, which is 1. And yeah, makes sense. We got it another way. And we didn't have to construct a sequence of partial sums to figure it out. I just realized that the dichotomy paradox was actually adding a geometric series. Pretty cool.
About that one.
Excuse me?
I have a question really quickly about that one. So
Yes.
when you start at the n minus 1, then you go to n and then n plus 1 and then n plus 2 and then so on and so forth. If you were trying to construct a series of partial sums, right?
Yeah.
Okay, just making sure you don't go the other way.
I'm not. So, I mean, last time we did this, that's what we did. We constructed a sequence of partial sums. So I said, okay, when I add up the first term, looks like that. When I add up the first 2 terms, first 3 terms, first 4 terms, then I got a bunch of numbers that I now had to figure out a pattern that connected all those numbers. And so I can talk about this. In general, the sequence of partial sums looks like that. And then I took a limit of that, right? However, what you'll notice with the geometric sequence is that I already played that game. I figured out for a geometric sequence, the sequence of partial sums always looks like this. And so when I take the limit, the answer is always going to look like that. So I kind of skipped past all that game of figuring out the partial sums. I just know whenever I see a series like this, it will add up to this under this condition, right? So it's like a shortcut. Like I didn't need to know, I didn't need to figure out the partial sums. Technically in the background, I already knew what they were. Like you can prove in general that the partial sums, the sequence of partial sums looks like this. But yeah, once you actually know that it's geometric, I know it's going to add up to a over 1 minus r. So I don't need to construct those partial sums and taking limits. I already know where that would lead me, and it leads me here, it leads me to a over 1 minus r. So that's another way to actually solve this, figure out what the series is.
And the only reason you start at r to the n minus 1 is so that you can get a on its own as the first term?
Right.
Okay.
So you would notice here, and another thing you'd realize, but when I started writing out this series, what you should notice is that the first term here is a, right? So the reason why I went through this trouble is that there's a common mistake that could be made here. I suppose I can write that down. When they see the series of a half to the n, starting at n equals 1, they would look at this as, oh, maybe it's a half to the n from n equals 1. And then they would think about this as, oh, maybe it's 1 times a half to the n. And so my a is 1 and my r is a half. And this is incorrect. Right? Because if you actually start writing this out, it's the first term should be a half, not 1. Right? So this here is your a. So it's very important that you have the right pattern. So I gave you a couple ways to interpret a geometric sequence. If it starts at 1 versus starting at 0, these are very different. You need to make sure you can identify the first term. And which means if it starts at 1, you want the power to be n minus 1, whereas if it starts at 0, you want the power to be 0. But that's just to make sure that you don't misidentify the first term. So I needed to make sure, because I know it started at 1, that my power is n minus 1. So that when I plug in 1, this is just a half to the 0, and I end up with my first term being a half.
Okay, thank you.
Yeah. Okay. This is also something that we can figure out using what we know about geometric series. Any ideas on how to deal with this one? One. Bueller.
Could you factor off 1/4 from the 4 to the n plus 1, because that's just 4 to the n times 4.
Okay. Can even bring that outside if I want. Okay, now what?
Wait, I'm sorry, I don't understand that.
4 to the n plus 1 is 4. So this, you realize it's 1 plus e to the n. 4 to the n plus 1 is actually 4 times 4 to the n.
Okay, yeah, I
Right,
got
so
it.
there's
Thank
like there's like a quarter, and we factored out the quarter.
you. Okay.
Okay,
Could we
which is
split it?
a move in the right direction, because we're starting at 0, right? We're starting at n equals 0, so we do want the power to look like n. Yeah. Now what?
Could we split it into 2 fractions? So 1 over 4 to the n plus e to the n over 4 to the n. And you can rewrite the second term as e over 4 to the n.
Can't you rewrite both of them? It's just
Yeah, so I can write this as 1 over 4 to the n, and this one I can write as e over 4 to the n. And then?
Is that equivalent to, this sounds like a calc mistake, but 1 plus e over 4 to the n?
Right, so that is an error. Like that's a distributing powers across sums error. So no, the 1 to the n plus the e to the n, you can't think of that as like 1 plus e all to the n, which is essentially what you're doing there.
I'm not sure if like this is the next step, but isn't anything to the power of 0 1?
Yes. Well, any non-zero thing to the power 0 is 1, yeah?
Right. So then like if you plugged in 0, you would get 2.
Yeah.
I'm not sure if like you do that. So then 2 times 1/4 is a half, which is less than 1.
Why would that matter?
We could find
Uh,
our A, right?
Huh? Come again?
If we plug in 0, can we find our A?
Before that, is this geometric?
Can we just like write it as 1/4 times the sum of 1/4 to the n plus 1/4 times the sum of e/4 to the n? So 2 summations.
Can distribute
then
the
the-
summations across the sum, right? So that was a property that we saw last time. This I can think of as 1/4 to the n plus the sum of e/4 to the n.
And it's not geometric.
What's not geometric?
Well, both of those. Well, the like 1/4 to the n and e/4 to the n, because they're both less than 1.
Right? So now they're geometric, each of these individually. So what is the A here? And what is your R?
A is 1, R is 1/4 for the first one, A is 1, R is e/4 for the second one.
So now these are geometric. So plugging in to figure out the first term in the last step was not something you would do, because with the sum, it's not geometric, right? The pattern of a geometric is this, right? It's not the sum of two terms. A geometric series is a series of a constant times another constant raised to the nth power. So the trick was to distribute the series, which we know we can do. That's a property of series. And then I can actually apply the geometric series to each term individually. Right, so this one is actually going to add up to A over 1 minus R plus A over 1 minus R. I can multiply out back the quarter. That's going to be 4 minus 1 plus 1 over 4 minus E. So it's actually a third over 4 minus E. So that does converge. Converges absolutely to 3 plus 1 over 4 minus E. So these were individually geometric. I will mention it here. So a very common error as well, common mistake, is to think of this as 1 plus E all to the n over 4 to the n. Then say A is 1 and your R is 1 plus E all over 4, right? That would actually be incorrect. And that's distributing powers across sums. You can't have the nth power. Like if you were to expand 1 plus E to the n, you get a bunch of terms. You don't just get the two terms. But yeah. Right, excellent. So that's geometric, and that's the kind of example where I would say a geometric series, it's kind of obvious, but at the same time not obvious, because you might have to do some algebra and maneuver things a little bit before you actually recognize it as a geometric term. But the moment you see like a constant raised to the n, right, you should start to think geometric. It's one of the first things. Anyway, like I said, when I get through all the series tests, I'll talk about strategy later on. Like, if you saw this in a random list of tests, why would you think geometric the first thing out of the other 10 things that I told you about, right? So we'll get to that. We'll get to strategy pretty soon. But yeah, that's how you would do with this one. Okay, what about this one?
So would you rewrite this like the last one? Would it be e divided by pi times pi to the n?
Okay. And then what?
You could pull out the e over pi.
Then?
Rewrite it as 1 times 1 over pi all raised to the n.
Right. And so that gives us what?
A
So this
equals
is
1, r equals 1 over pi.
so of course absolute value of r is less than 1 because 1 over pi is less than 1. And so this actually does converge to a over 1 minus r. A divided by 1 minus r. So that's e over pi minus 1. So that series converges to something interesting, e over pi minus 1. Look, Mao, we added up an infinite number of terms. This one.
The alternating plus and minus will tell us that our a is negative, probably.
Well, the r would be negative, right? So the a is
Oh,
just
right.
staying there. The r, when you're raising to powers, yeah, it'll change. So the r is negative, which means when you raise it to even powers, it'll be positive. When you raise it to odd powers, it'll be negative. Yeah, that would make sense. How do you identify them though? How do you even know this is geometric? Like besides the fact that we're in the section where I'm talking about geometric.
The numerator is increasing in powers of 3.
Mm-hmm.
So the numerator
Oh.
would be 3 to the n.
Okay. And the denominator?
Doesn't this one diverge? Because the terms.
Well, justify. How are you going to justify that diverges?
Well, because like I can't. Never mind.
I learned.
Well, wouldn't
R
your
to-
r be -3/2, which is greater than 1? Or the absolute value of it would be.
Right. So one thing you can notice is that this here, it's like, okay, so if I take 1 and then I multiplied 1 by -3/2, then I multiplied that by another -3/2. Then I multiplied that by another -3/2. Then I multiplied that by another -3/2. Right? Notice that that's what we actually have. right? So I keep multiplying by -3/2. So the second one's going to give me +9/4. The third one's going to give me -27/8, etc. This guy actually adds up. Guy is like a series where the first term is 1 and the R, the common ratio, I wrote that phrase in the notes, is that, where I can do it like that. Or, I mean, I could start it like from 0 to n. Either way, you would realize that here your A is 1 and your R is -3/2. So you would realize that this is a geometric series. With A equals 1 and R equals -3/2. What you can then note is that the absolute value of R, well, that's just the absolute value of 3/2, -3/2. Well, that's just 3/2, and that's bigger than 1. So the series diverges. Yeah, so that sum actually diverges, and you would figure that out by noticing that it's a geometric series and then realizing that the R is larger than 1 in absolute values. I think those are all the examples I had here. Right, so that's a geometric series. So it's another kind of series. And it has its own test to go along with it. You know that whenever you see such a series, you can determine whether it converges or diverges by that test. Figure out who the A is, figure out who the R is. If your R is less than 1 in absolute values, it will converge absolutely. If your R is greater than 1 in absolute values, it will diverge. You might need to do a little bit of arithmetic to get it into the right form, as examples B and C showed you. But ultimately, once you get it into that form, you can write it as A times R to the n-1 if you're starting from n equals 1, or you can write it as A times R to the n if you're starting from n equals 0. If you can write it in either of these forms, then you can consider it geometric. Your A and your R are constants, non-zero constants, and yeah. Okay, so that's the geometric series test. So that's another row crossed off of our table. So now we're going to do the integral test. Let's talk about the integral test. It's another test, another row in the table. So suppose you're given a series. And so it's a random series, sum of A to the n. And you realize that, you know what, if I think of the an as a formula, just think of it as a function of n, right, that I can plot on in the 2D plane or something, right? So it's a real valued function. Just imagine the real valued counterpart. Then it turns out you can determine how the series behaves based on how the corresponding integral behaves. And let's talk about that. So let's say you have this integral from a to infinity of f of x dx, right? So it's like you have some function. Let's say it's like this. This is your f of x. Someone got kicked out of the room. Let them back in. Say this is your f of x, right? And you know that if you were to find the area here, right? So the area is equal to the integral from a to infinity of f of x dx. This starts at a, right? So you imagine that you can plug in all the numbers and create a function. Now what you can also start to realize is that, well, if I were to only pretend that this guy only works on the integers, then I can sort of compare this to me drawing a bunch of rectangles, right? So I can compare it to like that, like that, like that, like that, right? And someone else might think, well, I could actually draw the rectangles the other way as well. So if I start here at A, A plus 1, A plus 2, etc. Talking about this area. Then I can maybe draw rectangles going like that, right? And so the thing is, and I'm not doing a proof, but I'm actually trying to explain to you the idea. I'm going to make a conclusion, and while I'm not going to prove it specifically to you, I just want you to get the idea of why, when I say that, it actually makes sense. You should realize, oh yeah, that does make sense, is because of this idea. You're kind of matching up this idea of Riemann sums with just a continuous area. And if you think of the area here as like A sub 1 and the area here as like A sub 2, then you realize that the Riemann sums are just like adding A1 plus A2 plus A3 plus A4 plus A5, right? And going on, so on and so forth. You can also notice a couple of things. Based on how we actually organize the rectangles, the area of the rectangles can either be underneath the curve or above the curve. And this will tell you two things. If the improper integral converges, meaning the area under the function is finite, the picture on the left will show you that the sum A1 plus A2 plus A3 is also going to be finite because it's going to be less than that answer. Whereas the picture on the right can tell you if the area under the curve is infinite, like it diverges, then the area of the rectangles, the sum of the areas of the rectangles will also have to go off to infinity. So you're in a situation where if the integral converges, then the series is going to converge. And if the integral diverges, then the series is going to diverge. And it turns out that when you're in a particular situation, you can actually make this comparison. Okay, so in this case, we can kind of see idea here. If a to infinity of f of x dx converges, then a1 plus a2 plus da 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 converges. And here you'll notice that if f of x dx diverges, then you can assume that the area, the sum of these areas also diverges. Okay. In other words, I can tell you what's going on with the series if I know what's going on with the integral. And at this point, we're all experts at taking improper integrals. So this is amazing news. This leads us to the integral test. This illustrates the idea behind this test here. So ultimately, you can prove that this leads to the following. It's called the integral test. So let A, the series of AN be any infinite series, right? And suppose I can think of my AN as a function, and the function satisfies these three qualities. One, f is continuous. I need it continuous because I want to be able to apply my knowledge of improper integrals on it, and I need the f to be continuous for me to apply the integration, for me to assume that the fundamental theorem of calculus is going to work and all that stuff. Okay, the f is eventually decreasing. This is necessary because if the f is increasing, the area is clearly going to diverge, so it should be decreasing. And it's always positive. And this is because I don't want to have to worry about integrals adding and subtracting, and giving me all sorts of weird answers, right? So as long as these three things are fulfilled, then the series and the integral, so the series AN and the integral a to infinity of f of x dx, they will actually behave very similarly. They will actually both converge or they will both diverge. And meaning, in this scenario, meaning under these conditions, we can determine the convergence or divergence of the series by determining the convergence or divergence of the integral. So this puts us in a situation where we can actually use calculus to help us make a determination, right? And this is just because of the interplay between Riemann sums. If I can construct rectangles in such a way, and you'll always be able to do this, that the area of the rectangles correspond to the magnitude of the terms of the series, then by someone constructing left-hand versus right-hand rules, you can show that the series and the integral are actually going to do the same thing. So sometimes you have a series and you're in this situation where you'll notice that, you know what, I could actually integrate that thing pretty easily, and it's decreasing, it's continuous, and it's always positive. It turns out that you can instead do an improper integral to talk about the series. So here's an example. Determine whether this series converges or diverges. So I have this series, pretty weird looking from the beginning. The series n goes from 1 to infinity of e to the 1 over nth power over n squared. Okay, now this looks kind of weird. However, notice that, imagine an equals some function f of n. This means that my function f of x would look like e to the 1 over x squared. Now, there are a couple things that you will notice about this. Note, f is continuous. On 1 to infinity, right? So I'm not dividing by 0. My exponential works. Everything else works. So we're continuous. 2, f is decreasing. How do I know f is decreasing? Well, I can actually find f prime. So that is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This cancels that. This will be minus e to the 1 over x times 1 plus 2x over x to the 4th. And my x here is greater than or equal to 1. So my exponential is always positive. 1 plus 2x is always positive when my x is greater than 1. X to the 4th is always positive. So I have the negative of a positive number. So this is less than 0. So this means it's decreasing. And it's actually non-negative. So it's continuous, it's decreasing, and it's non-negative. Notice those 3 conditions are fulfilled here, which means I can actually talk about the series by talking about the corresponding integral. Instead of looking at the series, n goes from 1 to infinity of e to the 1 over n squared, I can then look at the integral that. And at this point, I expect that should be something we should be able to actually handle. Does anyone see how we would handle that integral?
Wouldn't you pick u to be 1 over x?
Right, you can do a substitution, right? By substitution, you say u equals 1 over x. This means your du is going to be minus 1 over x squared. And so this will pretty much become the integral of e to the minus e to the u du. 1 over x squared dx. right? And so we know that that integral is just minus e to the 1 over x between 1 and infinity. And yes, I know I'm supposed to write the limit as blah, 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 and up there. And okay, we're big kids now. That was last week. We're now eating solid food. So of course you realize that when you plug in infinity, that's going to go to minus e to the 0. Plus when you plug in 1, you get that. So you get e minus 1. So this guy converges. Let me make some space here. So let's call this I. So this means I converges. And that means our series converges by the integral test. So once you're in this situation where you can think of the thing that you're finding the series of, if I imagine that was a real valued function, it will be continuous decreasing and positive, non-negative at least, right? It has to be greater than or equal to 0. Then if I know what happens to the corresponding integral, I will automatically know what happens to the series. So I can actually compute an improper integral, determine whether that converges, and then that will tell me that my series converges. If I had computed the improper integral and it diverged, it would tell me that my series diverged. But it's very important that you realize these have to be fulfilled. I have to stress that. Like you can't just do this with every series, right? Under these conditions, right? You have to check that all these things are true. Otherwise, it doesn't work because your integral itself might misbehave, and then you won't know what happens to the series. So yeah, that's the integral test. So, and again, I'll go over strategy later on, but essentially the idea is you see a series where you're looking at the thing and you're like, you know what, I could actually integrate that pretty easily. You can just see the substitution screaming at you. Then you're like, maybe the integral test would work. It's something that you can look for. So yeah, you see something like this, it's a very strange kind of thing, like what? But you just happen to notice, you know what, I could actually integrate that. And it wouldn't be that bad. It's a substitution. Then it might be worth you checking out if these 3 conditions hold. Because if they do, you're in luck. You can just integrate it and determine the answer, right? And so that's the integral test, pretty important test. This leads actually very nicely into another test called the P-series test. And so first of all, you can define a P-series. This is just a series of this form. So it has a very specific form. And I don't know if the size of the font here kind of messes it up. So let me actually rewrite this a little bit more clear. So a series that looks like this, where it's 1 over n to the power p, right? P is a constant. That is, such a series is called a P-series. Okay, so that's a definition. So P-series, a very specific, just like the geometric, it has a very specific form, 1 over n to the p. Now, what you would realize is, and I'm not going to write it out because I already typed it up here. If you think of an as 1 over n to the p as a function, then you're looking at the function 1 over x to the p. Notice that it's continuous, decreasing, and non-negative because 1 over x to the p is going to either look like this if your p is even, or it's going to look like that. And it might be the mirror image for you guys. I don't know. So you know how it's going to look. Like for positive x, it's always going to look like this. So it's decreasing. It's continuous because my denominator is not 0. And it's always above the x-axis for when you're on the right. So it turns out for this series, I can actually apply the integral test and I compare it to this integral. But it turns out we already know about that integral, don't we? the integral from 1 to infinity of 1 over x to the p dx converges if and only if my p is greater than 1. So it means that I can talk about when a p series would converge based on the integral test. But of course, now that I know that, I don't have to invoke the integral test all the time. I just know about the p series. So the series this guy converges if and only if p is greater than 1. Okay, so if I see a p series, all I have to do is identify it as a p series, then identify the p value. If the p is larger than 1, it's going to converge. If the p is smaller than 1, it's going to, if the p is smaller than or equal to 1, then it's going to diverge, right? And that I kind of know from the integral test. Now, what you can notice here is that this actually harkens back to an example that we looked at last time. So last time we looked at the harmonic series 1 over n, and we also looked at the series 1 over n squared. And I told you that the first one diverges and the second one converges. Notice that you can actually see that right away with the p series test. For the harmonic series, let me scroll back up here. Where did I do that? Yeah. So here, let me look at this example here. For the harmonic series, notice that on the left, the series of 1 over n, I can think of that as 1 over n to the 1 power. So the example D here is a p series where my p equals 1. On the right, I have the sum of 1 over n squared. This is a p series where my p equals 2. 2 is greater than 1, therefore the right side I know it's going to converge, but the left side I know it's going to diverge. And I can know that right off the bat because of the p series test, which is a consequence of the integral test. So I can use the integral test to prove the p series test. So the p series test is just a very specific application of the integral test, but it's a worthwhile application. It's something that you should know separately because p series are actually very convenient in general. And they're sort of convenient in the same way that that the corresponding integrals were convenient, the 1 over x to the p integral. Those guys came in handy when you wanted to make comparisons between two things. And so if you can compare it to a 1 over x to the p, and you know how that integral behaves, you can talk about the other integral, right? We're actually going to use p series in the same way. So it seems like a very specific kind of series, and it is. But the point is, we're hardly ever going to need the p series by itself alone. We're normally using a p series to compare it to some other series. So knowing how the p series will behave is going to be useful in that regard. And this is how the p series behaves. Yeah, so I have a couple of examples here because it's really not, at this point, it's not rocket science. The idea is essentially, so you have something like this. The series n goes from 1 to infinity of 1 over radical n. Just realize that I can rewrite this as n to the 1/2 and realize this is a p series. With p equals 1/2, which is less than 1. This means it diverges. So I can talk about this series and I can know that it diverges. So you see something like this one, and it's the same idea, really. Just realize, by laws of exponents, I can write this as 1 over n to the 11 over 10. And you realize this is a p series. With p equals 11 over 10, and that's bigger than 1. Therefore, it converges. by P series test. So yeah, a very specific scenario, 1 over n to a constant. If the constant is bigger than 1, it'll converge. If it's smaller than or equal to 1, it'll diverge. It's called the P series test. And it's very hard for me to give you a complicated example here because there really are none. But these guys come in handy once you can rewrite something as 1 over n to a constant, which in general is going to be easy to see. They come in really handy when you want to actually compare to something else. And to that end, that leads us into the comparison test. So we do have 2 comparison tests, a direct comparison test and a limit comparison test. And these guys are actually pretty analogous to the comparison tests for improper integrals. So the same idea applies. If you know the comparison test for improper integrals, you know the comparison test for series. It turns out that those tests work out if I replace the integrals with series. Who would have thought? Well, again, the integral test kind of tells us this, right? Because we know if I'm in a situation where I can compare the integrals to the series, then they're going to behave very similarly. So it turns out that the comparison theorems for improper integrals do apply to series. So suppose I have 2 series, an and bn, series of an, series of bn, and they obey this inequality. Then their summations obey that inequality, and I can actually make comparisons. If the larger series converges, then the smaller series must converge. And if the smaller series diverges, then the larger series must diverge. This is assuming both series are greater than or equal to 0. Then in any other scenario, I can make no conclusion, right? It's possible for the larger one to diverge while the smaller one can either diverge or converge, and vice versa. So yeah. So I can look at a series like this one, which looks very complicated, but the point is I want to not deal with that series. I want to deal with something simpler. So we can actually, just like with our intuition from improper integrals, I would know I would focus on the biggest guys because the smaller guys don't matter. And what I'm going to do is I would compare to this series. I want you to notice that I'm starting it from 1, because if I started k equals 0, I would divide by 0, and that's no bueno. But it's okay because here, if k equals 0, the ak is 0. So it is okay to start from 1. Otherwise, we can do that thing that we did with comparison theorem where you just evaluate a few terms and then you make sure that the series start off at the same term. And you could do that as well. And you can compare those two. But yeah, I can compare it to this, right? And I can actually simplify this. This is 3 over radical 2. And this would be k over k to the 5 over 2. So that would look like what? That would look like 2 over 2 minus 5 over 2, so that's minus 3 over 2. So this looks like 1 over k to the 3 over 2. Okay, so now I get a series, looks pretty complicated. I don't want to deal with all that. Ignore all the smaller guys, because if I'm going off to infinity, they're not going to matter as much. So now I can, in lieu of this series, I can consider a simpler series. But you want to know, can I consider this simpler series and actually talk about the other one? But it turns out that you can, right? Now you'd realize that if you set AK equals the original guy, and BK equals this new guy, then you actually have this relationship holds because the denominator on the right is smaller than the denominator on the left, so it's bigger. And so that means that this relationship holds. And I know on top of that, that BK is a convergent P series. Because my P is 3/2, which is greater than 1. So I can ignore members of the denominator to create a simpler series. Turns out that series happens to be a P series. And by knowing about the P series, which is easy to determine, I can actually tell you that AN converges. AK converges by comparison. Okay. So that's the comparison test. The limit comparison test has a similar idea, but I'm not going to go through that because we're pretty much out of time. But of course, the idea is when you can't determine the inequality, right, then you can try something like a limit comparison test. Okay. Yeah. So for now, we'll wrap up there. Again, I'll post the notes to this so you guys can even look ahead if you want, if you have time. But we'll wrap up there for now. So we now know up to the, go back up. So far we know about the geometric, the that, and that. So next time we'll pick up Monday. We should be able to finish the rest of the tests on Monday. And then on next week, Thursday, I would go into strategy and that sort of thing. Like, how do you know which test to pick? But yeah, we will stop there for now. So yeah, so a couple things. Like I said, I'm holding a general office hours like right now, or I guess we can all take a 10-minute break and come back. Maybe I can start at 7. You guys can go get a drink of water, stretch your legs or whatever. And we can start at 7 for a general office hours because I had a few people who wanted to meet with me after class, and we can just talk about whatever. So a few ideas might be to go over the review that I posted on the class webpage and or the fake quiz that I posted last week because you guys didn't have a quiz. So yeah, and just a heads up. So I know this week is terribly stressful for all of you guys. So I'm thinking like of not having a quiz next week as well, just to give you guys a little breather. And so probably in recitation, what you guys could do is go over the test. But yeah, we'll stop there. So stop there for now. If you want to join the general office hour, I sent out an email in Jupyter with the Zoom link there, and I will see you guys in a few minutes. That being said, the rest of you have a good night. Good luck tomorrow. Make sure you get a good night's sleep tonight as much as possible. Hopefully you've been studying up to this point. You don't want to pull an all-nighter with a class like this. You do want to keep your wits about you. That being said, we will stop there.
Thank you.
Okay, so good night, everyone. Have a good night. Good luck tomorrow, and I will see some of you in a few minutes. The rest of you, I'll see you guys when I see you in the next one.